The last potential, last one-dimensional potential we're going to do with the Schrodinger equation is the finite square well. And this is a good picture of it right here. At minus a and plus a, or between minus a and plus a, there's a potential of minus V0. Everywhere else it's a free particle. So that's how we write our potential. Immediately what we're going to find over time is that we get both bound and scattered states. Let's jump right in. Let's examine the region first where x is less than minus a, and that's where, of course, v of x is 0. So Schrodinger equation like so. I'm going to use kappa again, so to make the differential equation look a little bit nicer. Write this as is equal to kappa squared psi, where I'm going to define kappa by the square root of minus 2me over h bar. Solution, of course, again, psi of x is equal to a e to the minus kappa x plus b e to the plus kappa x. Of course, the only allowed solution is going to be b e to the positive kappa x, because at x equals minus infinity, the first term would blow up, so a has to be 0, and we just keep the second term. So we can write psi of x then as b e to the plus kappa x. Let's look at the region between minus a and plus a. In that case, my Schrodinger equation becomes minus h bar squared over 2m, second derivative of psi with respect to x, minus v0 psi is equal to v psi. And so I'm going to rewrite my equation. Second derivative of psi with respect to x is going to be equal to minus little l squared psi, where I'm going to define little l by the square root of 2m times e plus v0. Yeah, it just makes it look a little bit nicer. Well, of course, divided by h bar. L is going to be real and positive. My general solution, I'm going to write psi of x as c times the sine of L times k plus d times the cosine of, that should be L times x, d times the cosine of L times x. Then finally, for x greater than a, again, it looks like a free particle. And in this case, I can write my general solution as f e to the minus kx plus g e to the positive kappa x. But in that case, g has to be equal to 0, otherwise the wave function would blow up at infinity, a positive infinity. So therefore, I can write my solution in this area, in this region, as f e to the minus kappa x. Now let's apply boundary conditions. Once again, we expect that psi and d psi dx will be continuous, or must be continuous, at minus a and plus a, x equal minus a, x equal plus a. But we can make our lives a little bit simpler if we think about it this way. The potential, as you notice, is an even function. Just by looking at it, you can see that. Therefore, psi of x must have solutions that are either even or odd. This means that we can impose boundary conditions at x equals a, and those at x equal minus a automatically apply. So let's just look at x equals plus a. And notice, for continuity at x equals a, that must mean that f e to the minus kappa a must be equal to d times the cosine of L times a. Same is true for the derivative. That must mean that kappa f e to the minus kappa a will be equal to d times L times the sine of L. I got two negative signs, a negative sign on each side, just get rid of them. If I divide the second equation by the first equation, notice I'll get kappa is equal to L times the tangent of L times A. This equation tells us what the allowed energies are. It's not easily solved, however. It's a transcendental equation, and the way you solve it is either graphically or numerically. We'll look at sort of a graphical solution, even though it's rather cursory. Nonetheless, let's make some variable substitutions for convenience. Let's define z as L times A, and let's define z naught as A over h bar times the square root of 2m v naught. Okay, so we'll use those to make our equation look a bit nicer. That means that kappa times A can be written with those variable substitutions as z naught squared minus z squared. And so our transcendental equation becomes tan z is equal to the square root of z naught over z quantity squared minus 1, all under the radical. What that's going to look like, something like this. Pi over 5, 3 pi over 2, 3 pi, 5 pi over 2, 3 pi. I get asymptote of my tangent function. Of course, I get asymptotes at every one of these pi over 2s. So it's going to look like this. Every other one, right? Pi over 2s, I should say. And then my other function looks like so. And of course, everywhere the two solutions cross, everywhere the two lines cross, two functions cross, I should say, is a solution. You read them off the graph, and that will tell you what the solutions are. Not an easy thing to do, as I say. You're more likely to solve this numerically, but we won't do that at this level. We can, however, look at two limiting cases. So suppose we have a case where our well is wide and deep. If our well is wide and deep, that means that Z naught is very large. That means that my graphical intersections are going to occur just below. So my intersections will be just below n pi over 2 for n odd. In other words, it will look something like h bar squared L squared over 2m is equal to E plus V naught. Now, E plus V naught is basically the energy above the bottom of the well. And I can write that as n squared h bar squared I squared over 8ma squared. These, of course, are my infinite square well energies, or at least half of them. So as V0 approaches infinity, we have an infinite well, but only a finite number of bound states, so long as V0 remains finite. So that's one possibility. Another extreme possibility is to say, suppose we have a shallow and narrow well. Let's look at that. In the case of a shallow, narrow well, as Z0 decreases, you'll have fewer bound states. Until, for Z0 less than pi over 2, you get only one bound state remaining. Now, there will always be at least one bound state, regardless of how deep the well is. But let's look at the scattering states. Bound states are only half the issue. Let's see what our scattering states look like. So in this case, E is greater than 0. For x less than minus a, we get psi of x is equal to a e to the kappa x plus b e to the minus kappa x. E to the ikx, e to the minus ikx, where k, using k, not kappa, k is defined as square root 2me over h bar. If I'm inside the well, so minus a less than x less than a, then I'm going to find that psi of x is equal to c sine of Lx plus d cosine Lx, where we define L as the square root of 2me plus v0, all divided by h bar. And then for x greater than a, assuming that your wave is not incoming from the right, we'll just talk about from the left, so psi of x is equal to f e to the I kx. So with all of these, we're going to have 4 boundary conditions. So psi at x equal minus a, if I equate the two equations at x equals minus a, I get x a e to the minus I kx plus b e to the I kx, a ka and ka is equal to minus c sine of La plus d cosine of La. d psi dx at x equals minus a gives me I k times a e to the minus I ka minus b e to the I ka is equal to L times c cosine, first derivative La, plus d sine La. The other side, psi at x equals a, gives me c sine La is equal to plus d cosine La is equal to f e to the I ka. d psi dx at x equals a gives me c L cosine La minus dl sine LA equals I K F e to the I K. Now, with all those boundary conditions and a whole lot of algebra, I can combine and solve again for a transmission coefficient and a reflection coefficient. And it turns out after a ton of algebra, solve for my reflection coefficient, B is going to be equal to I over 2KL sine 2LA times L squared minus K squared times F. This gives me F equals e to the minus I, 2IKA times A divided by the cosine of 2LA minus I sine 2LA divided by 2KL times the quantity L squared plus K squared. I told you the algebra was a mess. And so from here I can calculate a transmission coefficient, F over A squared, and I'll get something, I'll write it as a reciprocal. T to the minus 1 is, of course, A squared over F squared, and that's going to be 1 plus B naught squared over 4E plus B naught sine squared of 2A over H bar squared square root 2M E plus B naught. Now, when this argument is equal to n pi, any integer times pi, of course, my transmission coefficient is going to be 0. And it's going to be equal to 1 whenever E plus V naught is equal to n squared pi squared H bar squared over 2m times 2a naught squared. So those are the conditions on my transmission coefficient. A lot of algebra to get here, but at least you can see we can look at the scattering states and the bound states for the finite square well. And that's really all I want to say about solutions for the one-dimensional Schrodinger equation. Next time we're going to start solving the Schrodinger equation in 3 dimensions, and of course that's going to culminate in solving the hydrogen atom.